Hey, good morning. Still learning how to use this, but this will be our first supporting video to lecture 13. And I try to go over one in-lecture example with you for the turbine calculation. Let's start with this. Supporting video. Lecture 13. This is a slide roughly around 14 example of turbine. So for the turbine calculation, we'd better recall what would be the working equation in order to use. As we discussed in that lecture, if I have a turbine, and I'm going to have some inlet, I'm going to have outlet, and then the main purpose is I'm going to receive some shaft work over there. So for any flow process, the starting equation would be the first law of thermal. You recall the first law of thermal for flow process. Then we would easily have delta H is, the general format would be delta H plus kinetic energy change plus potential energy change would be heat and shaft work. I want to remind you that here this delta U square is actually delta, no, not delta, it's U2 square minus U1 square. Right? Is it clear? It's almost there. Here, let's see, this is delta much better. Delta U is indeed U2 square minus U1. Right? So that if that is the case, then as we discussed in lecture, we have the assumption that we are not going to change potential energy, and then the pipe, the tube, the velocity of the flow will not be changing too much. So this one goes 0. And then the whole purpose of having a turbine is to receive as much shaft work as possible. So this term goes 0. Try to have this adiabatic process. So then for a turbine, later on we also discussed that it's actually the same working function for pump or compressor or expander. We would have the same working equation. Delta H is shaft work. Right? And then we say, well, this is a 1 unit of this heat engine or Carnot cycle. We say if reversible, meaning indicating Q reverse is 0. Able to read it. That implies, meaning S, this delta S will be 0. Therefore, we are going to have delta H yes. The second S over here is the so-called isentropic process. Meaning entropy does not change. Alright, so this is the fundamental equation when you are working on a turbine or expander to receive some shaft work. On the other end, the reversible process will be pump or compressor. You try to provide some shaft work, and then you are going to change entropy of the working fluid. So that is more or less the general idea of those calculations. Now let's take a look at the example. Get rid of this. So now we have this on slide 14. The problem says that we are going to have a steam turbine with rated capacity of 56,400 kilowatts, operates with steam at the inlet condition of I better keep the turbine. This is inlet, T1 is 8600 kilopascal, and then temperature. No, this is T1. T1 is 500 degrees C. Then we are going to have a discharge into a condenser at a pressure of 10 kPa. This is to condenser. Outlet, P2 will be 10 kPa. How about T2? No idea for now. Then we know the turbine efficiency is 0.75 efficiency. That much. Then we want to determine the state of the steam at discharge and the mass rate of flow of the steam. So we want to understand so for this outlet, the state of the steam, and also mass rate of flow. Right. So here, what does it mean by the state of the steam? So in general, if we want to determine the state, then we need to understand T, P, and X. X is coming from the ratio, is usually the ratio of vapor and liquid. Okay, so that itself is actually a hint that we are going to have a mixture of the outlet, or we can safely assume this is a wet or saturated. Steam. By wet, by saturated, we mean we are going to have vapor and liquid simultaneously in the outlet. And it's actually making sense, because this is why we only need to have this P2. So for this one component, two phase, if you apply Gibbs-Phillips rule, F is n minus pi, F is n minus pi plus 2. If this is wet steam, 1 as water, 2 as phase, then we only need one descriptor to describe the system completely. So that assumption is quite solid, it appears. And then we need to somehow combine those three conditions and solve this problem. So now the question is how we are going to use that efficiency. We have developed the understanding that for the steam, this is superheated, very likely, and this is why we need to have two descriptors to determine the state of that superheated steam. And we are going to use the steam table again for the saturated steam to look up some other constants, enthalpy, entropy for the corresponding vapor, corresponding liquid state. So we know generally how we are going to use the TP conditions over there. But what about the efficiency of this turbine? So if you recall, as we discussed on slide 13 for the turbine efficiency. So the efficiency is indeed discussed by using this HS diagram. So let's use another there. HS diagram. This is H, this is S. So we say I'm going to have two pressure. This is P1, this is P2. So for the turbine or expander, we are going to start with hot or a fluid with larger enthalpy. So this is my starting initial. And then I'm going to assume this isentropic process. This is the maximum efficiency. That's not the reality. So this is why we call this as 2 prime. Along this process, you can see that the entropy is not changing. This line is perpendicular to this entropy x. And we know that the real final state will be here. Let's call this as 1. This will be 2. Alright? We can see that this is my corresponding H1. This is my corresponding H2 prime. That itself is my actual H2. So the efficiency is defined as delta H, let's call this as real, over delta H along this isentropic process, or this is real is delta H. Here we are looking at this numerical value. So this is why it's not final minus initial, but we are using H1 minus H2. Or if you want, you can take the absolute value and H1 minus H2 prime. Right? So then, of course, we need to figure out vapor over liquid ratio of that state. Right? So then we start with the known condition, the known initial condition. Using the steam table, we can get rid of some writing over there. Get rid of this. Are you able to read? Hope so. Now if we start this one, and I understand from steam table, so this is using superheated steam table. We can quickly receive this H1 and S1. Again, here I'm going to have pure vapor. So as I have, H1 is 3391.6 kilojoule per kilogram. S1 is 6.6858 kilojoule per kilogram Kelvin. And now if you come back to this, I'd better keep this HS diagram. 1, 2, 1, 2 prime. This is my actual 2. So I figured H1, and I know S1. So now if we use this isentropic process, S1 is also the same as S2 prime. Okay. So I'm going to have this state 2 prime, which is also wet, meaning vapor plus liquid. And I know its total entropy S2 prime, which is coming from S2 okay, S2 of this liquid, okay, plus S2 of that vapor. But I need to figure out their ratio. Okay, so this is why I have on this slide 15. I said let's try to assume the ratio would be x2 prime. It's not the real final of state 2. It's the isentropic state of 2 prime. So this is why I was using x2 prime, which is the ratio of vapor over liquid. Okay. So now if I combine x2 prime and I want to set up the actual equation, then I would have at this 10 kPa look up the saturated steam table. I would have vapor. It's H, vapor, S, vapor, and I could also have this corresponding liquid at that pressure condition. H, liquid, S, liquid. So now with the values as I have, this S vapor would be 8.1511 kilojoule per kilogram Kelvin. S vapor, no, excuse me, this is wrong. Liquid is having smaller entropy because they are not that crazy. 6493. The entropy of the vapor is larger, 81511 kilojoule per kilogram Kelvin. And I also have this corresponding entropy. This is the liquid, 191.8 kilojoule per kilogram. And this itself is slightly running out of space. Get rid of this. This is liquid. This is 2,584.8 kilojoule per kilogram. Yes. So now if I have this x2 as their ratio and I know the total S2 prime, then I can set up that equation, which is S2 prime will be S2L plus X2 prime S2 vapor minus S2L. So from this equation, if you have zero vapor when X2 prime goes 0, then I'm going to have pure liquid. So that is a good and correct equation. So by using that, and we know S2 prime, which is a total, which is the same as S1 along this isentropic process. S2 at that liquid phase, we have this value over here. S2 vapor is also known from the saturated steam table. So all the entropies are known so that we can solve for X2 prime. Okay. So what we have been doing is we try to figure out that I'm going to have wet steam along this isentropic process, and I'm also having, let's call this X2 prime, the actual wet steam at this real final called X2. So using the isentropic process, we are able to solve for this x2 prime. So with that information, then we can use this x2 ratio. Now I have this x2. Then I can calculate what would it be h2 prime. Okay. Once we figure out x2 prime, then we can set up this equation. This h2 prime will be h2 at that isentropic final state liquid plus x2 prime h2 vapor minus h2 liquid. And the h2 vapor, h2 liquid will be coming from the steam table over here. Right? This is again the saturated steam. So at this 10 K Pascal, we are able to get those values from the saturated steam table. And x2 prime was coming from the previous calculation. So this is how we can solve and figure out what would be my h2 prime. By knowing h2 prime, then I can calculate this delta H along isentropic process. The absolute numerical value is H1 minus H2 prime. Okay. Now I have this also solved. I have this solved. What's the point of doing this? So now this is known. This delta H along the isentropic process. If this is known, then as we did, let's visit the efficiency, which is delta H real over delta H isentropic process. Real is H1 minus H2. Isentropic is H1 minus H2 prime. So we have this H1 from steam table known. H2 prime we just solved over here. This is from table. This is solved. This is known from problem statement. So now if you put all those values into this equation via the efficiency, then we are able to solve H2, which is the actual final enthalpy of wet steam, a mixture of vapor and liquid. We have this calculated. However, if you go back to this diagram over there, we have figured out H2 of that mixture, but we don't know what is the X2 value, the ratio between the vapor and liquid of the actual final. However, we can calculate that. Why? This H2 is simply, if we are doing the mixture calculation of vapor and liquid, and assuming their ratio is X2, again X2 is vapor over liquid. Then we can have this H2 of liquid plus that x2 of the real final H2 vapor minus H2 over liquid. So now if you check on this equation, we have H2 of the real wet mixture, we have this calculated from here. And we are able to read this from the steam table. Still this is 10 kPa of liquid, 10 kPa of saturated vapor in that steam. This is also known. So we have all those known. Therefore, we are able to solve x2. Right? So if we have this x2, then we understand what is the state of the outlet. This is because now we know for the outlet, now we know P2. P2 is from the problem statement, and using the saturated steam table, we can read the corresponding temperature too. And also I know this is a wet, vapor, and liquid coexistence. Their ratio is x2. I know all those three key parameters to describe my system. Right? So this is the first part of the calculation. The second part is the mass flow rate. Why we need to have that mass flow rate? This is simply because now if you try to take a closer look at that H2, using the steam table, we are going to use the unit of kilojoule per kilogram. This is the enthalpy unit. However, we are using this, the requested shaft work is expressed as kilowatt, which is, I'm going to get rid of some part over here. This H2 is the actual enthalpy of the final. Therefore, I know delta H real, which is the actual shaft work. Yes, H1 minus H2 in the unit of kilojoule per kilogram from the calculation, right? In the problem statement, we are going to have the shaft work as kilojoule watt per second, which is kilowatt, right? So now we need to take a look at this is kilojoule per second on the left hand side. On the right hand side, I'm going to have kilojoule per kilogram. So I'm missing something as kilojoule per second in order to satisfy the units. And what is that? Kilojoule per second. This is indeed mass flow rate. Right? So therefore, we are going to set up the calculation as the actual shaft work in kilowatt is H1 minus H2 times this mass flow rate. I'm using a dot to represent the flow rate. So this is why I'm having on the slide 17 the calculation of minus or I can take this as a positive because we are looking at the actual numerical value. If I use minus, then I stick with the sign definition. That would be H2 final minus initial times mass flow rate. This H2 is from my previous calculation is 2,436 minus this is from the inlet steam table 3,000 times. You're gonna have this positive mass flow rate. Right? This is another double check on your calculation to see if you have the right sign definition. So this is how we solve this whole problem of turbine, knowing inlet, knowing outlet, knowing the efficiency. And we need to figure out two critical values. One is along this isentropic process for that wet steam, what would be the ratio of vapor and liquid. And we also want to have this same ratio for the actual final state too. And by having a clear understanding of the final, then we can manipulate all sorts of questions. To somehow summarize the flow rate of the calculation, I'll try my best to describe a general procedure. So the procedure here is we know, let's take a look at a known value. Known is T inlet. Very often we are going to have this superheated steam. So we are going to have T1 and P1 provided to us. No. So from there, we are going to get H1 and S1. Okay. Now, following this process, using S1, I'm going to have S2 prime, same as S1. This is from this isentropic process. And S1 is the outlet along this isentropic process, where normally we are going to have this saturated steam, vapor plus liquid. Furthermore, X is defined as vapor over liquid. Okay. So here there you would have a T2 or P2. So by having T2 or P2, we are going to have vapor corresponding pure vapor HV, H2V, entropy to V, liquid. H2L, S2L. Okay. So now, if you have this S2 prime over there, we are going to figure out S2 prime would be S2 liquid plus X2 prime S2 vapor minus S2 liquid. Okay, so from here I'm going to solve X2 prime. And using this X2 prime, then I can solve H2 prime, yes, H2 liquid plus X2 prime, H2 vapor minus H2 liquid. So I have this solved. Moving forward, using the efficiency definition, delta H, delta HS, yes, H1 minus H2, H1 minus H2 prime, then I have this H2 prime solved. Okay. So now I should be able to have the actual H2. I'm going to set up a similar equation like for the isentropic final state. H2 will be H2 of this liquid plus, now I'm going to have this actual X2, H2 vapor minus H2 liquid. And I should be able to solve X2. Okay? So now I can tell what my final state of the outlet. So here I also know the efficiency. That's a nice, quite neat diagram. Okay. So let me take a photo of this before clean it up. But I think that is the first example I want to have, and I'll double check the quality of the video, and we'll go from there. Thank you for watching.